Let's look at a chi-square test of independence. Is there a relationship between the color of a driver's motorcycle helmet and whether the driver is injured or killed in a crash? Here are some data. Color of helmet. These were the people who were not injured in crashes. These were the people who were injured or killed in crashes. So is there a relationship between color and whether a person is not injured or injured or killed? Recall that earlier we used a chi-square goodness of fit test when we divided our counts into different categories according to one categorical variable. The categorical variable was the leading digit on the check amount, and we had 9 categories. This is what it looked like. So again, 9 different categories, one categorical variable. Here we have 2 categorical variables. We have the color of the helmet and whether the person was not injured or killed. To determine if these categorical variables are independent of each other, we use a chi-square test of independence. By the way, a table like this with 2 categorical variables is called a contingency table. Okay, find null and alternative hypotheses. The null hypothesis, as always, means no difference, no effect. The row and column variables are independent. Row has no impact on column, or vice versa. Alternative hypothesis is that there is a difference, there is an effect. The row and column variables are not independent. In this case, this means the null hypothesis is that the color of the helmet and the likelihood of injury or death are independent. The alternative is that color of helmet and likelihood of injury or death are not independent. In other words, they're dependent. Okay, we want to do a chi-square test of independence. Do the data satisfy the required conditions? Here are the conditions. Counted data condition. The data are given as counts, not measurements or percentages. So it can't be a measurement of pounds or feet or something like that. It's got to be something that we count. And we have that. We're counting deaths and injuries, etc. Expected cell frequency. The expected values for each cell are all at least 5. Randomization. Yeah, it appears to be pretty random. 10% condition. The sample's total less than 10% of the population. You bet. All of those are satisfied. Okay, calculate the test statistic. This again is a chi-square test. Same formula, except the expected frequency is the row total times the column total over the grand total. You'll see in a moment what I mean by that. Okay, so here's our chart. These would be these are our column totals here. These are our row totals. That would be our grand total, 1553. So if color of helmet and injury were independent, the expected frequency for the top left cell, so black helmet, not injured, the expected frequency in this cell would be the row total times the column total over the grand total. In other words, 1124 times 704 divided by 1553. And when you calculate that, you get 509.5. So if the two were truly independent, color of helmet and injury status, then the expected would be 509.5. You could repeat that for all of those. You just sum up the observed minus the expected squared all over the expected. So that'd be 491 minus 509.5 squared over 509.5. You just do it for all of those cells. Oh my goodness, you could do that. Is there a way to find this test statistic chi-squared on a graphing calculator? Yes! We can do this on a TI-83, TI-84, etc. by entering the data into a matrix. That's a rectangular array of numbers, as you will see on the next page. So I'm going to go over this briefly, and then I'll show you how to do it. So you press matrix, that's above the X inverse key, edit, and enter. This enters data into matrix A. The dimensions of the matrix are the number of rows by the number of columns. Ours is a 2 by 5 matrix, right? So we've got 2 rows and 5 columns. So our data are in a 2 by 5 matrix. Use enter or arrow keys to enter numbers, press quit, press stat, tests, chi-square test. Our observed values are in matrix A, and the expected values will automatically be in matrix B. That is very cool. And then you choose calculate. So let me show you how we do this. Okay, let me show you how we do this. So we turn the TI on, press stat, press matrix, and then we got to get edit. So edit. So we're going to put stuff in matrix A. A is a 2 by 5 matrix, so 2, enter, 5, enter. And now we just enter these numbers. 491, enter. 377, enter. 31, enter. 170, enter. And 55, enter. And now it automatically goes to the second row. 213, enter. 112, enter. 8, enter. 70, enter. And then 26. Okay, now we quit. So our data are in there. That's great. So now we go to Stat, Tests, and we want the chi-square test. Not the chi-square goodness of fitness test, but just the chi-square test. So this will be the chi-square test of independence. Okay, the observed are in A, the expected are in B. Now we just choose calculate. Bam, there we have it. So our chi-square test statistic is 9.97, our p-value 0.04. Okay. Determine whether we should reject or fail to reject the null hypothesis. Use a 0.05 level of significance. Okay, so if you didn't know that the p-level was, 0.04, or that the p-value, I should say, not the p-level, the p-value is 0.04, here's how you do it. The rejection region is chi-square is greater than chi-square star, where chi-square star is from the table at the back of the book. Chi-square tests are always one-sided tests. Okay, so we look at the chi-square test. It's in the back of the book, or we could just enter chi-square table in a search engine. That's another way to access the information. Okay, so here's a chi-square table. The column is 0.05. That's our significance level. The row is the number of rows. And the row we want in this, now it's the degrees of freedom. So it's the number of rows minus 1 times the number of columns minus 1. That's 2 minus 1 times 5 minus 1, which is 1 times 4. In other words, 4. So we look at row 4, and it looks like 9.488. That's our value of chi-square star. Okay, our value of chi-square is 9.9712, which is greater than chi-square star, the critical value of chi-square. So we conclude that the null hypothesis is false. We reject the null hypothesis. Color of helmet and likelihood of injury or death are not independent. Find the p-value. Well, we've already seen one way to do it. You could just use that hypothesis test. Here's another way to do it. We want the area to the right of chi-square equals 9.9712. This is what a chi-square distribution looks like when there are 4 degrees of freedom. So basically, we want the chi-square notation. Again, this is available under Dister on your calculator. This is your left endpoint, A, your right endpoint is B, and your degrees of freedom. In this case, our left endpoint, we want to know the area to the right of 9.9712, so that would be our left endpoint, 9.9712. The right endpoint is infinity, but there is no infinity button on the calculator, so we just enter something really big, like 100,000. Degrees of freedom is 4. And then we press enter, and we get 0.0409. That is our p-value. If the p is low, the null must go. We reject H0, because our p-value was less than 0.05. And we would say there is some evidence to conclude that color of helmet and likelihood of injury or death are not independent. And that's because it's pretty close to 0.05. We can't say there is strong evidence. We just say there is some evidence. Okay, and that 0.0409, that's the same p-value we got when we used the graphing calculator. According to the Insurance Institute for Highway Safety, motorcycles are less stable and less visible than cars. When motorcycles crash, their riders lack the protection of an enclosed vehicle, so they're more likely to be injured or killed. On a per-mile basis in 2014 in the United States, the number of deaths on motorcycles was 27 times the number in cars. And again, that's on a per-mile basis.